Hello, everyone, and welcome. I'm going to just start this thing off by introducing Tom here and what we're talking about today. We've all seen stories about climate change. We talked a little bit here as we were waiting about movies like The Inconvenient Truth and places like your Facebook feed where most people get information about it. And we've also seen a lot of people say time and time again that we're not doing anything about climate change. That simply is not true. There are a lot of products out there that lessen dependence on fossil fuels and cut down on emissions. And one of those solutions we're talking about today, all electric heat pumps. All electric heat pumps have been shown to lower energy costs and lessen our dependence on fossil fuels that many say contribute to climate change. So today, Tom Jolene is going to lead a scientific discussion about the prospects of heat pumps to replace furnaces in cold climates like ours here in Wisconsin, and how it fits in with the whole climate change debate. Now we know that you're going to have some questions along the way. And when you do, you can simply post them in the Q&A or the chat, and we'll get to them at the end of the presentation. So without further ado, here's Tom. Tom, take it away.
All right. Thanks, Eric. Thanks to all of you for coming. Maybe there's 5 of you or 50, I have no idea, but either way, this is great stuff. So a heat pump future in this presentation, let me just talk about what I'm hoping to accomplish. It's not to sell a bunch of heat pumps. What it really is, I was having a conversation with a neighbor a little while ago, and I was like, hey, maybe a heat pump for your home. And I said, if you're curious about it, come to our website and check out the videos. And the next time I saw him, what he said was, that was really cool. All of a sudden, I'm much more curious about climate change and heat pumps and where I'm spending my fuel dollars and all that kind of stuff. And that really is a great outcome. And I'm hoping for the rest of you that if you're just maybe getting near the opening of the rabbit hole, you're willing to go a little bit further. And the science side of it is I'm not a scientist, but I just kind of climbed into this rabbit hole myself a little while ago. I didn't know anything about any of this, maybe as soon as 2 years ago. And so all this information is very findable. And I thought it would be a good place to start because I think most people have a limited working knowledge about all the subjects that revolve around climate change and all those types of things. So without further ado, if you wonder about climate change, you're not alone. So this is a poll done by Pew Research. Pew Research is not a climate-based interested organization. They just conduct surveys about polarizing subjects. And so if I was going to summarize this slide in a few words, would be that lots and lots of people kind of have in the back of their heads some concerns about climate change. Some people are completely indifferent and don't feel any concern about it at all, and that may be true. But then how are we dealing with it as a government or a society? Well, those in the, kind of a mixed bag. Some people feel stronger. Some people feel like there's a lot more room to go. So this is sort of the United States general feeling about climate change. And because climate change politics is driven by government, it becomes a polarizing conversation. So the goal here is to say, let's just forget about which side of the aisle you might land on and just say, let's just look at the math and let's look at the science behind it and try to make our best educated decisions on those bases instead of just which way we lean. This will be the only slide about climate change. That white layer above the earth is trapped greenhouse gases. And I think we can all agree that this is sort of well-known science and that the radiation that's created by the sun reflects off the earth but gets trapped by the greenhouse gas layer and has some effect on the temperature of the earth. And we're going to get into that a little bit right now. So where is this research coming from? And so if you, like I've watched some talk shows before and they'll say the scientists say this and that and the other thing. And I always kind of wondered who these random scientists were and how they gathered up all their thoughts and where they agreed this percentage or that percent, this or that percentage of people who say, scientists who say this or that. So there is a group called the IPCC, the Intergovernmental Panel on Climate Change. That's a mouthful, but it is a nonpartisan group that is made up by members all over the world. They do no research at all. All they do is gather up the studies of others, review the efficacy of the studies, and decide whether or not to include it, along with hundreds and thousands of other studies that are performed around the world by independent groups or government-sponsored groups, or all the climate data that's out there. They gather it all up. So in April of this year, they produced a report. Now, I will be perfectly honest with you and say that 1,300-page report is out of my league, as is the 150-page technical summary. However, the 42-page summary for policymakers is not an exciting read, but it is interesting. If you ever decide to check out more about the IPCC, their FAQ page is marvelous. Lots of great information, very searchable, easy to gather information. So this organization was formed in 1988. So let's go back in our heads. Some of you might not have even been around in 1988. For those of us who remember, the internet was in its infancy, and computer power was, while at that time much greater than it had been 20 years previous, is a far cry from where it is now. So what they've been able to do in the past, 30 some odd years, is definitely build far better models and do much better in the way of prediction to see if humans are affecting the climate. In 1990, their first report, they could not say, either it wasn't conclusive or they didn't have the methods to make an assumption that humans had an impact on climate. So this latest report that came out, like I said, in April of this year, says, hopefully you guys can see this on your screens. I have to look at this one to read it, but A1, point number 1, it is unequivocal that human influence has warmed the atmosphere, ocean, and land. So those of you who are hoping for an easy way out of this discussion, the IPCC would not agree with you. What's really interesting in this chart on the left shows that we've kind of been a little bit lucky. If you remember the ozone layer discussions in the 80s and 90s, the hole in the ozone layer has actually contributed to global cooling, while the greenhouse gases has contributed to global heating. So the net effect is actually of greenhouse gases has been reduced by the depletion of the ozone layer. So maybe we're a little bit lucky. We bought ourselves a little bit more time. It's probably not good that the ozone layer has been compromised, but on the other hand, maybe we're allowing some of that heat to translate out of our atmosphere. So the most conclusive report by IPCC thus far, and more data is going to come from those folks, not only with, that was raw data, and then next steps, and just there's a lot of information on the IPCC site. So in order to understand greenhouse gases, well, in order to have any context on the IPCC, we got to know about greenhouse gases. So all this information is just very researchable, a lot of great stuff on EIA, which is a very comprehensive government report on the use of fossil fuels and electricity. So if we look at this slide now, we've got our US grid, right? So when you plug in your computer or your light or whatever it is, the US average is that 20% of that grid is made up of renewables, which is really exciting. And 20% of it is also made from nuclear energy, which may surprise you. Maybe not so surprising is that we still have quite a bit of coal on the grid, and that almost half, well, 40% of the grid is powered by natural gas. So renewables and nuclear energy create no greenhouse gases, and 60% of the grid does. What makes up the grid as far as the fuels that we use to create electricity and just to straight out burn them, like for example, natural gas is what powers the furnace in my home. If you live just a few miles to the north, your furnace may be powered by oil or LP gas. And you'll notice that in this chart, the effective greenhouse, well, the amount of greenhouse gases created by different fuel sources, you can see here, hard coal is nearly double what natural gas is. Natural gas has been a wonderful thing to prevent greenhouse gas escalation because it is a cleaner fuel. And when people say, hey, natural gas is a cleaner fuel, this is exactly what they mean. And it's sort of a fun fact that certain types of wood, if you have a wood burning stove, is considered no greenhouse gas because the wood grows back. Okay, so now we know where this greenhouse gas comes from burning fuel. Let's look at all the power in the United States. So this is a much more comprehensive slide that might be a little bit difficult to follow, but let's just take a couple minutes here and boil it down. If you look on the left, these are all the inputs, okay? So solar electricity is dedicated strictly to electricity generation. That's the only thing that it does. Whereas natural gas is partially used for electricity generation and partially used in the industrial segment. So on the left is all the inputs, on the right in the pink is all the outputs. And then you'll notice one of the sad things about the way we produce energy is 2/3 of the energy is waste heat. Now, some of that waste heat is recovered, but most of it, unfortunately, goes to atmosphere. So when we add renewables to the grid, there is generally no waste heat that's in some kind of a mass form. So adding renewables to this is going to make our overall grid quality better, certainly from the greenhouse gas emissions, but also from the efficiency side of things. So if we look at how we're doing locally, you may have a little bit different picture. So this is my cute little play on Badgers versus Gophers. I've been keeping up with the folks in Minneapolis. They are ahead of the game when it comes to climate change than we are here in Wisconsin, although the folks in Dane County are catching up pretty quickly. If you look at the third from the bottom, the renewables that are being used in Wisconsin compared to Minnesota, we're kind of pretty far off. We have a long way to go. There's way more dedication in Minnesota towards climate change, and you can solve it. But we're just a couple of years behind, and I think we'll have to catch up. But what does that mean? It kind of means that the quality of our grid, so when you electrify in Wisconsin, like let's back up a little bit. 30% of the grid in California is powered by renewables. So when you plug your plug into the wall, you're actually producing less carbon than when you plug your plug into the wall in Wisconsin. So it is a combined effort to get the grid quality better with more renewables baked into it. So this is just a side-by-side comparison of a couple different states. Now, as a homeowner, and maybe you're not a homeowner or a business person or someone who's active in this discussion, what can you do that actually has an impact when it comes to this subject? There's all sorts of other subjects about what you eat and do you carry your bags to the grocery store, and we're going to leave that stuff to the side for the moment. We're just going to talk about this fuel source opportunity here. So I'm going to thank my neighbor John in advance for sharing some information. He purchased 12 kW of solar for his home. Now it's on the backside of his house, so I don't get to see it when I walk my dogs past his house, but he was willing to share this information with me. So it produces, now what's cool about solar, just as a sidebar, is it's pretty bulletproof. When they say you're going to produce this much electricity, that's exactly what it does. I have a 114 kilowatt installation on my roof, and it is like within a couple percentage points of what they say they're going to produce to what they actually produce. It's very predictable. Now, when you use a kilowatt hour of electricity in Wisconsin, it creates 1.23 pounds of CO2, which seems like a lot, doesn't it? For 1 kilowatt hour of electricity. But that's how much greenhouse gas it produces. So John, by putting this solar array on his house, will save 18,541 pounds of CO2 every year. So great job, John. It wasn't cheap, $21,000 after his rebates. So John got pretty creative with his time of day metering, because if you're producing enough solar power during the day, what he does is pays a higher rate during the day where he needs almost no electricity from the grid. And at nighttime, when the sun goes down, he pays a lower rate. So he's managed to make his payback about 10 years. And I'll talk a little bit about home powered paybacks in just a second. Okay, so now if I drive a 2014 Honda Pilot, I drive a Honda Pilot because my kids are 6 feet tall and I'm 6'3" myself, so I'm not going to be able to pull myself into a Honda Insight. At any rate, over the course of a year, I drive 15,000 miles, which produces quite a bit of carbon, 6.3 metric tons. If you use the Tesla calculator and then kind of cross-check it against other methods and use the carbon footprint of the grid in Wisconsin. So in other words, if you drive a Tesla in California, you do better than if you drive a Tesla in Wisconsin. So it'll produce 2.7 metric tons of CO2. There is some cost difference if I have to replace my car. And so there's some cost difference between this Model Y, which is a more expensive Tesla than some of the others. But there is fuel savings every year. But we're talking mostly about carbon footprint, and we're cutting our footprint in half. So in that big grid that we looked at a little while ago, we're making some progress down here in the transportation section, and maybe not as much in the residential and commercial sections. So going back, okay. And it's interesting that it costs you about 5 cents per mile to drive a Tesla, which is pretty cool. And I'm not advertising Tesla, whoever's electric vehicle, their data was just easy to get my arms around. So there's a payback to it. It's long, but it's there. Okay. Now we're going to talk about heat pumps a little bit, and keep in mind, I'm going to come back to this with a little more in-depth on this, where these numbers come from, because it's not completely transparent. These numbers are based on an energy model. An engineer friend of mine named Jeff has an Energy Star house. And in order to have an Energy Star house, you have to use the geothermal heat pump, which is really cool, and compared it to a code compliant. So if you're going to build a home, you have to have minimum a 92%, maybe it's 94% now, furnace, and a 13-SEER air conditioner. If you do use equipment that's lower than that, you don't meet code, you'll have a hard time getting a permit. So after we boiled down the usage of the HVAC system, the heating and cooling, the code compliance system required about 6,000 kilowatt hours a year, and 266 therms. Therm of energy is 100,000 BTUs. So BTUs and watts are interchangeable through a calculation of it's just a conversion factor. Whereas this heat pump that I've kind of got this picture of, and we'll see some more pictures in a minute, we required 7,600 kilowatt hours, no therms. So the carbon footprint here and here are very similar. There's some small reduction. And there was some utility savings. So there was a payback here, similar to what John produced with his solar array. So we're going to come back to that in greater detail in a little bit. Okay. What's interesting about heat pumps is the math is very challenging. And it's not challenging as in, oh, you need to learn differential equations. It's just challenging in the number of variables required to solve the problem. So for example, every heat pump manufacturer has different performance information. And even with the heat pump manufacturer, they may have different models, and then each size has different performance features. Of course, your fuel cost, if you live a few miles north of us, you might be using LP or oil, like I mentioned before. that changes the equation on whether or not a heat pump makes sense for you. At what point do you switch to a backup? We're going to talk about backups here in a little bit. What's your actual loading on your house? Like how much heat do you need to maintain 70 degrees or whatever your set point is? Can you isolate your fuel sources? For example, you get one electric bill that has your lights on it, your microwave oven, and your furnace powered by it in your air conditioner. So can you partition those out? Difficult to do. And then do you do anything weird like open up your windows in the summertime? That happens in my house sometimes. Okay, so one thing to think of when it comes to financing long payback projects is if you use the business mindset of a 5-year payback or a 3-year payback, you may struggle. But when you're looking at a home improvement that has a 10-year payback, you can look at it 2 ways. 10 years is a long time, I might not live here. The other way to look at it is say, all right, there are mortgages out there that will allow you to borrow more than the value of your home. So let's say you bought a $200,000 home, you could get mortgages that are green up to $230,000 and use that 30 grand for home improvements. So as you're financing that home at whatever the low rates are, 3-4% or something like that, maybe even lower, you're getting a 10-year return plus it's all post-tax. So quite a bit more benefit than what you can out of the traditional savings mutual fund market. So for a financial savvy person, this is a really great way to go, and it'll be a cash flow positive thing as long as you're in the house. And if you sell the house, if you drove past the house in the 70s and you saw solar panels on it, you'd be like, if I bought that house, I'd take those solar panels down. They're ugly. Now you see solar panels on a house and you go, oh, that's cool. And they're worth something. And the value sticks to a house. Same thing with the quality of the HVAC system as we become more and more versed in how efficient our equipment is in our home. Okay, so a little bit more about heat pumps for those of you who don't know a lot about heat pumps, and you're not alone. So we're going to go nice and slow. In the summertime, you have most likely an air conditioner, and that air conditioner extracts heat from your home and pushes it outside and out of this outdoor unit. In the wintertime, that function operates in reverse. And it's a little bit crazy to think about, but even when it's -10 or -20 outside, there's still enough heat in the air to boil the refrigerant that runs through this circuit inside and outside. I use the example in the summertime with a refrigerator. A refrigerator keeps the box, keeps your produce cold, and then it dumps the heat into the house. Then your air conditioner takes the heat of the house and dumps it outside. We're just running that process completely in reverse, but it becomes more challenging because the colder it is outside, the more energy it takes to create this refrigeration cycle. Basically, you're boiling the refrigerant with very cold air. So when it's really cold out, it takes more energy and it boils less of the refrigerant to make the process work. But that's a heat pump. So let's look at a map of the United States. In the South, do you have to worry about how cold it is outside for heat? No, you don't have to worry about it at all. That heat pump works all year round. Now, this middle swath of the United States, there are going to be times when your heat pump just kind of can't keep up when it gets really cold outside. So there are advanced tech heat pumps that have, let's keep it simple, higher tech refrigeration piping to allow it to operate efficiently at low ambient conditions when it's cold outside. Now you get up here into the upper Midwest and you go, oh boy, we really have some challenges using heat pumps. Now, if you're going to take this circle, and it actually would be a little bit lower, but in this circle, if we were a separate country, the upper Midwest, so Michigan, Minnesota, Wisconsin, Iowa, Illinois, Indiana, North Dakota, South Dakota, we would be the 5th or 6th largest gas user in the world if we were our own country. We're baked into the United States, but we're by far the biggest gas users. So we're sort of at the center point of this discussion about heat pumps in converting our grid to, or converting our fuel sources to more electricity. Okay, so let's keep moving on. Because it's challenging, some cities have taken on climate action plans. I know there's some folks that are going to be looking at this from Ann Arbor. Minneapolis is doing a great job, in Dane County. In Milwaukee, there is a website that says, you know, we have a climate action plan, but their effectiveness so far has something to be desired. Why are they doing this? Well, they recognize that IPCC, those leaders received that 42-page summary for policymakers saying, hey, if we don't do something, there may be negative results here in the not too distant future. And we have a window to do something about it. So they're taking some action. Now, we have to look at some terms in heating and air conditioning that are going to be, we need to know them for background. So when you have a furnace, if your furnace from the 1970s might be 80% efficient, and now you may have a furnace that's 94 or 99, all those different types of efficiencies. And that's like, wow, that is really efficient. You can't get much more efficient than 90 some odd percent. But let's put a little context here. When you use electric heat, it's 100% efficient. There's no waste because basically there's no products of combustion. You know, in your home, when you burn gas, you have to take the flue outside, and that's loss. You're taking gas and you're turning it into heat plus carbon dioxide plus water. So that's considered the waste. Okay, so what about a heat pump? Heat pump has a little bit different math. And in order to facilitate that, I kind of have this chart that helps. So your furnace is somewhere between 80 and 96, 97% efficient. So when you take that fuel source, that's the output that you get. If you use straight electric heat, now when I say straight electric heat, electric baseboard, electric resistance heater, very few of us use those in our houses, and I'll show you in a little bit why that is. This heat pump, the Kingham heat pump I'm using specifically here, has a COP, a coefficient of performance, which means when I put 1 kilowatt of energy into it, I get a larger number of cooling or heating energy out of it. And I'm going to show you that in this next slide. Okay, so this is a heat pump chart. This is from our manufacturer. This is for a 3-ton heat pump. So let's take a look at this chart and see what it means. When it's 32 degrees outside and the temperature indoors is 70 degrees, the heat pump has a COP of 2.2, which means you put 1 kilowatt hour of energy into it, you get 2.2 kilowatt hours of cooling energy out of it, which would be converted to BTUs. And then BTUs turn into how big is my air conditioning unit, right? So depending on the temperature on any given day, the efficiency of an air source heat pump changes, thus complications in the math. But as you can see from the previous slide, there's always a benefit to using a heat pump from an efficiency standpoint. We're not talking about cost standpoint because that depends on your fuel source, but from an efficiency standpoint, this heat pump's doing a great job. Now, as the temperature gets colder, you notice that that COP is dropping. So the capacity is in BTUs. I don't know if you guys can see my mouse. The capacity is in BTUs and the power is in watts. So this ratio of COP is just the watts divided by the capacity in the same mathematical terms. So as it gets colder outside, the heat pump isn't much more efficient than straight electric, right? And the other concern is that that heat pump is supposed to be, this is a 3-ton unit, so 3 tons, 12,000 BTUs per ton, is supposed to put out 36,000 BTUs of heat. When it gets cold outside, wait a minute, it's only producing 18,000 BTUs. Does that mean it's a bad heat pump? No, it just means that the refrigerant is boiling at a lower rate, so we're not getting the full capacity of the heat pump. So that's going to lead to other things, other challenges that we're going to talk about. What the government likes is the efficiency of this heat pump when it comes to fossil fuels. And so in Wisconsin, if you have a rated, it's got to be AHRI rated. We're in the process of getting ours rated. It should be done in January. If you have a code compliant heat pump, and it's got to be this very high efficiency rating and this high heat pump performance level, they'll give you $1,000 towards your heat pump retrofit. So they're telling you something here. They want to convert more of the grid to electric to comply with that other stuff we talked about with the IPCC. Has a lot of this been done yet? No, it hasn't. Are we going to get there? Maybe with a little bit of education. Okay, now this next slide we're going to spend a few minutes on. I kind of half-baked modeled my own house. And the fun part about doing this thing is you never know exactly where you're going to land after you jump out of the airplane. And so some compelling things, some not so compelling things. This is just the raw math, and you guys can start making your own decisions. So this first example, hey, Eric, is my mouse showing up here? Do you see it? Or do I need to move it over here?
Sorry about that. I am not. Oh, yeah, I am seeing it
Here?
right now. Yep, right on the
okay,
top.
Okay, great.
Yeah.
Okay, perfect. All right, so my home, it was built in 2008, so it's 13 years old. When you get your gas and electric bill, it's all the gas in your house, right? So your hot water heater, if you have a gas dryer, if you have a gas fireplace, any other gas appliances, it's all lumped into a big pile. So we made some assumptions and figured out that to heat my home over the course of the year, we'd use 800 therms. So 800 times 100,000 BTUs per, yeah. So that's the therms. A therm costs about $1. It goes up and down. Last year was subsidized because of the pandemic. And the carbon footprint is also something you can pull off the website, off the EIV websites, for how much is the carbon footprint of a therm of gas. So here to heat, I'm producing 9,300 pounds of CO2 every year. Now, in my home, in probably your home, you have a separate air conditioner, not a heat pump. So we can look at the difference between summer and winter conditions and say, okay, seems about 6,000 kilowatt hours I'm using towards air conditioning my house. With the 13 SEER appliance, that turns out to be $660 and is about 7,380 pounds of CO2. Now, if you look at these two numbers, it kind of makes sense because we have a little bit longer heating season than other areas in the country. So if I total this up, costs me, and this is without the furnace fan, we use that as a constant. So just the heating and the cooling, heating through therms and cooling through kilowatt hours, it costs about $1,500 to run those systems over a year, and it produced 16,000 pounds, almost 17,000 pounds of CO2. And we're going to get to the stuff on the bottom a little bit later. Okay. Now, let's say that I want to do the right thing and power up my home using electricity, straight electric resistance heat. So I put baseboards in every room instead of having a furnace. And I could do that. How would that come out? Well, the bad news would be that you'd use a lot more electricity. Your carbon footprint would be significantly worse. Your air conditioning costs would be about the same, but your carbon, look at here, your carbon footprint has doubled by using straight electric heat. Because, at some point in the future, maybe our grid will be 100% renewable and that carbon footprint will be zero. But we're not at that point. Our grid's kind of dirty and it produces a lot of CO2 from plugging in. All right, now let's get a little bit deeper here. If we were to rip out my furnace and not have gas available, I could put in an 18 SEER heat pump, would be 4 tons, and have backup heating. Now, if we went back to that slide a couple ago, what we did, and this is some assumptions, we assume that over the course of the heating season, the average COP is about 2. We could debate that all day long, but there isn't a lot of great test data for multiple installations all over the area that we can build an average. We just have the factory test data. So I'm making a conservative estimate that a 3-ton unit would be about a 2. A 4-ton is a little bit more efficient. So again, pretty conservative. In this same model, we convert our therms to kilowatt hours. And in a future seminar, I'll just show you how this math goes. But it's 11,000 kilowatt hours plus our air conditioning mode of the heat pump is more efficient. It's 18 SEER versus 13 SEER. It's a straight ratio. So in the wintertime, we've produced quite a bit more CO2 CO2 than in the furnace model, but we've produced less during the cooling season. So what does that mean? Our operating cost goes up a little bit, and our carbon footprint goes up. So we're close. We can do heat pumps, yes. Is it really producing a benefit now? Not now. More on that in a second. If we go to dual fuel, so same heat pump, except in the wintertime, I'm going to leave that furnace in place, and when it gets really cold outside, I'll use the furnace and turn off the heat pump, just for efficiency. In this case, we're producing we only need 240 therms to get through this iteration. And the switchover temperature in this model is 17 degrees. So it hits 17 degrees outside, we turn the gas on. Above 17 degrees, we're using the heat pump. Below 17 degrees, it's gas. Okay. The electric usage for heating goes down from 11,000 to just 6,000. What we've done here is taken a look at that COP average at 70 from this chart before. So the COP average, if I cut out the minus 22, which we really don't, isn't our bin data, minus 15 happens a couple of hours a year. We spend a teeny little bit of time at minus 5, but if I cut that out and just look at 17 degrees up to 59 degrees, then the average is pretty, you could say it's maybe even a little bit higher than 2.5, but that's where I got that number from. Okay, so as we boil this all down, in the summertime, we're more efficient in air conditioning mode, and we have actually reduced by not a small amount the carbon footprint, and we've also reduced our operating cost some. Now, as our carbon, that's really the wrong nomenclature, but as our grid becomes more based on renewables, let's say when Wisconsin hits the national average of 20%, these ratios all change. Our carbon footprint drops more significantly in the heat pump model than it does in the gas model. Now we're targeting 50% renewables by 2050, and some municipalities are trying to get there by 2030, which I think is awesome. You can see that the impact of having furnaces is greatly diminished, whereas we've taken out 60% of the carbon footprint by having this heat pump. So that's part of the link in the chain is what we're trying to create. Okay, so that's the math. Now, again, any of those variables that we changes this entire chart, which is probably why heat pumps are a little bit more difficult for adoption and why we need more education. Okay. Now, if you were to call up your local contractor and say, hey, I'd like a heat pump, they'd say you're nuts, or they might say you're nuts. And I've experienced this firsthand. I had to drag some contractors kicking and screaming into a heat pump installation that we wanted to do. What is different about this tech? Well, I told you before that it's difficult to boil refrigerant when it's really cold outside. This compressor is built in a mass production fashion, can handle temperatures down to minus 31. Yes, it produces less heat, but it still can operate in your home safely. It's also variable speed, so the efficiency goes up greatly with a variable speed compressor. So it's matching the load. As your home gets colder, it doesn't turn on and off, it just speeds up the compressor to produce more heat. Okay. In an all-electric cold climate installation, if you have propane or oil, this is still using a straight electric system is more cost efficient than using propane or oil because of the fuel cost. So when it gets really cold outside, this little heater that's built into the top of the unit comes on and supplements the already operating heat pump. when it gets cold outside, you'll need some backup heat. Now notice that 2-ton unit is extremely efficient. And we'll talk about that more for multifamily in a future presentation, but you almost don't need any backup. Our design temperature in Milwaukee is -11. Really, you shouldn't need any backup heat. Could you have it? Sure, if you want to. But you can see that even at -22 degrees, some backup heat, not enough to ruin your electrical panel, is required, but it's not that much. Okay. Alternatively, instead of a straight electric system, if you're going to keep, you probably have gas pipe to your house, you can, this is kind of a good drawing of it. The furnace stays in place. You remove the coil, the air conditioning coil from the top, and you replace it with a heat pump coil. The only difference is the heat pump coil is built a little bit more stoutly because the pressures are higher. You take your boxy air conditioner, you need a stand, you put the heat pump outside, and that's it. So it's a one-day job for a contractor. I would also share with you that this heat pump on first cost, if you would compare it to a similar efficient air conditioner, should be less expensive. Okay. If your house has a boiler or you're going to do your 3-season room, this ultra heat compressor from King Home is available in a multi-zone system. So let's say you had boilers and you had a living room, a kitchen, and 3 bedrooms. You can put one of these wall units in every room and have it all piped to one outdoor unit, which has the same compressor in it, works the same way. Or for your 3-season room, let's make it a 4-season room. This can be used for one room and it'll operate year-round. Okay. And then if you really want to get off the grid, there are methods. You've heard of heat pump water heaters. This is a more efficient than a heat pump water heater, but it's a little more ornate in that it makes hot water, and then you can put that hot water into your hot water heater tank. So right now we're not using these, but at some point in the future, as people really get off of gas, this is going to be a solution to a problem that they'll have. Well, I can go to an electric dryer, and I'm going to need something for my water heater, and I don't want to go straight electric. What am I going to do? I'll go to a heat pump water heater. And with that, I think we've come to the end, and it's, oh, wow, 50 minutes almost exactly. Love it. It says contact your local distributor. We have not yet found a distributor. These education pieces are going to probably get us there. But in the meantime, you can call Airflow, and our brand is this all-season heat pump. We have Airflow website, and we have an all-season heat pump website that Eric administers for us. So did we end up with any Q&A stuff, Eric?
We did. And to everyone that you can post your questions either in chat or by clicking Q&A. And I'm guessing that there's a lot out there because, Tom, you went through just a ton of information in 45 minutes. So far, we do have one question. This one is from Dave. So a fuel system will reduce my carbon footprint and reduce my operating costs? Question mark.
Yes. And let's just go back to that slide from a little bit ago, because there was a lot there and it took a little bit of time to put it all together. But now let's just preface this. Mm-hmm. You can change all the variables here. If you don't turn your heat pump on, if you turn your heat pump off and use gas at different temperatures, you can make it more economical. On the other hand, if you're the kind of let's say you're John and you have a solar array on your roof, and you want as much electrical output as you can and use that gas as limited as possible, you're almost never going to have that heat pump shut off until it gets so cold. So you can vary all these variables to fit your specific. But if you don't have a solar array and you wanted the best dollar economy, you would run your heat pump in air conditioning mode, and until maybe 32 or 35 degrees, that would make those that total cost of operation go down a little bit. What else you got, Eric?
All right, so another one came in. It's from John. This with a 12 to 14-year-old furnace AC system, what is recommended for the blower system? Just replacing the exchanger and condenser is only part piece of a system that might be. All right.
I think I get the gist of the
Get
question.
the gist of that. Okay.
Should I replace my whole furnace? And the answer is, it depends. So a furnace is a pretty simple device. Let's see if I think did I have a slide on a furnace here? I don't think I did. Shoot. Sorry about that. So a furnace is a blower and a gas-fired heat exchanger. And there's an inducer motor to pull the products of combustion out of the furnace. So you can go to a lot of houses where the furnaces last 20 or 30 years.
Right.
In the case of a heat pump retrofit, how many hours are you going to be using the furnace? The furnace itself, the gas-fired part of it, not much. Then what's inside of that is an EC motor, electronically commutated motor, and a blower wheel. So in the event that your furnace died, it would be one of a handful of things. It could be the blower and the motor, but those EC motors, man, they last and last and last. And they're not particularly expensive. For me, with my 13-year-old house, I'm leaving the furnace.
Okay.
And use the blower that's there, because the value of the furnace, I'm going to be running my heat pump as long as I can. I'm barely ever going to be using that thing.
Okay. All right. So we got another question here. This is from Josh. If I were to change to dual fuel, do I need to change my thermostat?
Oh, that's a good question. The answer is yes. It needs to be a heat pump thermostat. So, and I'm not going to get into all the nuts and bolts of it, but somebody needs to take a look at the controls. Like in my house, I have a zone first zoning system. So I got to make sure that it's heat pump compatible, which it is. And I have to make sure, when the contractor comes in to do it, if you have a single zone, yeah, you can change out that thermostat. You also have to check the wiring to make sure that you have enough wires pulled back and forth. But any HVAC contractor should know how to run a heat pump thermostat. And if they don't, it's time to get a different contractor.
All right, good to know. That's all we have on questions. Tom, is there anything else you'd like to touch on?
No, just plan to look out for some seminars in the not too distant future. I want to talk about multifamily for sure, because that's a great bang for the buck for heat pumps and how that can be applied maybe for more, what would you call it? Social impact is multifamily. And then two is let's, dig into some of these heat pump calculations and see how we arrived at it, because you may need to do some of it on your own to justify. You may want to play the what if game, but if you can figure out where your fuel sources are and how to apply it to this, to a heat pump, and maybe find out that it's worth doing.
All right. So, yeah. We did have one quick question that came in from Steve. Is there a HW coil option for backup? And then he clarified to pair with the rad floor system slide you presented.
Ooh, is there a water coil? Well, I would say that's a really good question. If you have a water coil, that implies that you have a boiler. And the idea behind this heat pump, hydro box, water heater solution would be that you don't have a boiler. If you had a boiler, similar to what we're doing with the dual fuel, you could have your boiler as a backup. In which case, you would have to have your contractor see about putting a coil into that system. Usually a coil is for an air system, so I'm wondering about that. But you can also just email me the question, and I can handle that one offline.
Okay, and what's your email address?
Sure, very good. My email is tom@airflowreps.com, just like it sounds, airflowreps.com.
Okay, all right, and I posted that email address in chat. So I think that means we're going to wrap up for today. You have any more questions? Email Tom at airflowreps.com. And thank you everybody for attending today. This was a lot of fun. And Tom, thank you for putting this together.
Thanks, everybody. Appreciate your time.
All right, you guys take care.